Okay, welcome back. Number 6 is a lot like number 5, it's just backwards. So we're starting with 2 natural log of x plus 1/2 natural log of 9 minus 3 natural log of 2. And we're trying to use these same properties to, instead of pull this apart, push it back together. So the nice thing is you kind of follow your order of operations. Order of operations says do multiplications first. Well, what can we do with multiplications? Well, we can turn the multiplication up into an exponent. So this becomes the natural log of x squared as that 2 comes up, plus the natural log of 9 to the 1/2. We do have to remember what 1/2 powers do. And natural log of 2, bring that 3 up, 2 to the 3rd. You can bring the negative 2 or the negative with it if you want, as long as you turn that into a plus. Okay, great. Now we've got the natural log of this plus that. Well, what can we do with the addition of logs? Well, with the addition of the logs, it turns into the log of the product. So you get the natural log of x squared and 1/2 power. 1/2 powers are square roots, so we could write that as the square root of 9 minus the natural log of 2 to the 3rd. 2 to the 3rd is 8. Square root of 9, we might as well simplify it while we are here. Square root of 9 is 3x squared. Reverse the order just because I like it that way. Minus the natural log of 8. Again, now we have a log minus a log. Well, when you're subtracting 2 logs, they turn into the log of the quotient of the arguments. Natural log of 3x squared divided by 8. Be very careful. This is not the natural log of 3x squared over the natural log of 8. That would be the change of base formula. It is the log of the quotient. So the natural log of this argument divided by that argument. So 3x squared over 8. And that's your condensed version. So I mentioned that when we're in calculus, being able to expand this into simpler pieces often makes it easier to use some of our calculus tools on. But having it in this condensed form usually makes it easier to do things like solving techniques and sometimes graphing. So it's really helpful to be able to go both directions with these types of problems. Okay, that was number 6. Know these relationships. So, number 7. Solving now, we got a logarithmic expression. 14 equals 19 minus 4 natural log of 2x minus 5. Excuse me. So just like most of your other solving, we've got something complicated here. This natural log of 2x minus 5 is certainly where the meat of this problem is happening. So isolate it. Get the 19 out of there. Get the negative 4 out of there. So you can isolate the thing that's causing trouble. So I'm going to do that. I'm going to subtract the 19, negative 5 equals negative 4, natural log of 2x minus 5. Divide by the negative 4, divide by the negative 4. 5/4 equals the natural log of 2x minus 5. So once we have that isolated, we can handle the log. Now, how do we handle the logarithm? Well, this is log base e. We don't write it, the e, we just write ln, but there is a little e down there. So we can change forms here. Remember, this is saying that e to the 5/4 power has to equal 2x minus 5. Anytime you have y equals log base b of x. We talked about this a little while ago. This says b to what power makes x? B to the y power makes x. So e to the 5/4 has to equal the 2x minus 5. Or you can use things like the one-to-one property, raise take e to both powers. The e and the natural log undo each other on this side. Either way, you end up with e to the 5/4 equaling 2x minus 5. Well, then we can just solve for x. Get a nice exact answer. Add the 5, add the 5. E to the 5/4 plus 5 equals 2x. Divide by the 2, divide by the 2. And e to the 5/4 plus 5 over 2 equals x. And that is a nice exact answer. The solution set that you look at online turns the whole thing into a decimal. I think it ends up with, something like x equals 3.25 to, no, 4.25. Yeah, 4.25. And that's a nice decimal approximation, but you should be able to, if asked to give an exact answer, give that exact answer. E to the 5/4 plus 5 over 2 is a fine and reasonable solution to a problem like this. Being able to find decimal approximations is also nice, but be able to give exact answers when requested. So, 8 is actually fairly similar. Again, you're given a logarithmic statement. It's base 4 this time. X plus 14 equals 3. So again, the same type of principle. This is saying the logarithmic statement asks 4 to what power is x plus 14? Well, 4 to the 3rd power is x plus 14. And people often like to think of it as that 4 swinging to the other side and pushing that 3 up. Again, this is like, if you have log base 2 of 8, that says 2 to what power makes 8? Well, 2 to the 3rd, because if you swing that 2 under, 8 equals 2 to the 3rd power. Swing it back, log base 2 of 8 equals 3. Swing the 2 back. You can go back and forth like this. Always a true statement. So we can just change forms from this logarithmic form to the exponential form. Now it might be nice to know what 4 to the 3rd is. So it's 64. Yeah, 64. Subtract the 14, subtract the 14. By the way, this x equals 64 minus 14 stage, we've turned this addition statement into a subtraction statement. It's the same idea as turning this logarithmic statement into an exponential statement. We're building the inverse statement. We built the inverse statement by moving over the 14, by moving over the 4. It's the same exact kind of logic. So x equals 50. It is important to check. The last problem also, it would be important to check. Make sure if you put the 50 in for x, it doesn't make something negative. That happens sometimes. Be sure you're checking those answers. But 50 plus 14 certainly isn't negative, so it's a perfectly valid answer. If ever something becomes negative by the time it hits a log, you've got to throw it out. So it's just a nice thing to always kind of be aware that you're checking. Okay, number 9. Again, solve. We've got 3 to the 2x minus, these are 4 equals 16. So, not to be a broken record, but again, you could solve this in a couple of different ways. One, you could move the 3 over and have this as 2x minus 4 equals log base 3 of 16 and solve from there. But then you'll end up having to use change of base formula or something like change of base formula to get a nice solution. So I wouldn't tend to recommend that. And that is what's on your the solutions if you look on the online. That's a not unreasonable way to do it. But I want to show you have alternatives. You guys want to work on becoming more and more flexible. One of the things that we could do is apply the one-to-one property of logarithms and take the log with any base of both sides here. Now, why would we want to introduce a logarithm? We have something nice that doesn't have logarithms in it. Why would we put a logarithm in? Well, it's the exact same reason as when you have like 3x equals 5, you divide by 3. Why do you put in division? Because it undoes the multiplication. We'd put in a logarithm because it undoes the exponentials. What that gives you access to is your power property. It allows you to bring this down. 2x minus 4 times the natural log of 3 equals the natural log of 16. Now you can solve this nicely for x. You can either divide the natural log of 3 off, or you can just distribute it. 2x natural log of 3 minus 4 natural log of 3 equals natural log of 16. Add the 4 natural log of 3, so you get 2x natural log of 3 equals natural log of 16 plus 4 natural log of 3. Divide by the 2 and the natural log of 3. Divide by the 2 and the natural log of 3. And you get a nice x equals the natural log of 16 plus 4 natural log of 3 over 2 natural log of 3. Which again, the solution you had, oops, sorry, I got a little squish down there. The solution you have online, on the solutions that I gave you online, they were actually done by Doug, turns that log base 3 of 16 here directly into a decimal and just solves it. And that's great if you're wanting a decimal approximation and you know the approximation you want. The nice thing about being able to do it this way is you get an exact answer. This answer is accurate to an infinite number of decimal places. As soon as you round that number, you're only accurate to actually a little bit less than what you rounded that to. So again, like the other problem, you want to be able to answer in the exact form as well. So you want to make sure you're practicing that. Number 10 is kind of an extreme example of that. You can do number 10, or you could do number 10 the way it's listed, and you would get a fine decimal approximation. But I am going to ask you to do some of these as exact values. So you need to be able to do this, not only do it with decimals, but you should be able to do this with full-on logarithms, no decimal approximation, don't touch your calculator kind of manner. So to do that, we want to solve this using just either the natural log or the common log. I think the version on your online thing does the common log. I'm going to use it as the natural log. I really did want to give you guys a couple different ways of looking at these problems. That's why you have the two different versions. So again, I'm going to take the natural log of both sides. The reason we want to put in the logarithm is because logarithms, by their nature, undo exponents. That's their job, just like we put in division to undo multiplication. The different thing here is we're able to take the logarithm of any base that we want because of the power property. That way we can do it in base 5, so when we want to turn it into a decimal, we're already in a logarithm that we know. The point of putting in the log mechanically is to get access to the power property so we can bring these down. Do be careful, bring them down in parentheses. Times the natural log of 5 equals x plus 3 times the natural log of 4. Now, here's where people often get a little stuck, but keep in mind, if this was a 5 instead, or if this was, say, a 7 and that was an 11, you would distribute the 11 and you distribute the 7. Natural log of 5 and natural log of 4 are just numbers. Treat them like they're numbers. I don't know what the natural log of 5 is off the top of my head. It's a little bit, what is it, a little bit less than 2 probably. Natural log of 4 is even a little bit less than that, but somewhere a little more than 2 or around there. But these are just the numbers. If you knew this number, you would distribute it. If you knew this number, you would distribute it. So don't change that. Distribute that natural log of 5. You get 3x natural log of 5 plus the natural log of 5. Distribute the natural log of 4. X times the natural log of 4 plus 3 natural log of 4. It looks a little ugly, I'll grant you, but this is part of what you're getting used to, is what these things look like and how they behave. So now you've got, an x over here, an x over here. That's just a constant. That's just a constant. So get all your x's on one side, all your constants on the other. So I'm going to subtract the x natural log of 4 and get 3x natural log of 5 minus x natural log of 4. And I'm going to subtract the natural log of 5 on both sides. Oops. So on this side, we've got 3 natural log of 4 minus natural log of 5. That way we have all the x terms on this side, all the constant terms on this side. Now these can be, look like how am I going to collect these terms when I've got natural log of 5 here, natural log of 4 here? Well, that x is in every term, so factor it out. That's the key that everybody forgets. So, put a big gold star next to that. A big gold star that lights up and flashes. Because it's how we have to solve these things. Or lots of things like this. When you don't have like terms that you can collect, you need to be able to factor out that variable. The nice thing is, once you do, you can just divide off all that stuff. Divide off all that stuff. Get x equals 3 natural log of 4 minus natural log of 5 over 3 natural log of 5 minus natural log of 4. And again, that's an exact answer. If you're, moving satellites around and you need your answer correct to the 100 millionth decimal place, which is not uncommon. Well, not the 100 millionth decimal place, but the 100 millionth place. That's only, 6, 7, 8, 9, 10 decimals, something like that. 100 million, so 8 decimal places. So it's real common to need that level of accuracy nowadays. If you're doing anything subatomic, even just trying to build things like DVDs, DVRs, cell phones, often we need huge levels of accuracy. So being able to work in exact values, this thing is accurate to the infinitely many decimal places. As soon as you go to a decimal approximation, anywhere in a problem, you have limited your amount of accuracy. So while the sample does go ahead, and if you're asked to solve to 3 decimal places, go ahead and round when you want to. I would round to 4 or 5 decimal places until you're done, by the way. The one online doesn't do that. But being able to work in exact values is very important. So make sure you practice doing that. I know I've said that in the last couple of problems, but I don't want anybody to get to the test and go, oh my gosh, I didn't know we'd have to find exact values, or didn't know what that meant. Exact values means don't touch your calculator. It's the short version anyway. Okay, let's see. What do I have next here? Do I want to do that? No, I think I'm going to start with another video. Okay, I will see you soon.